Once we go to the moon, we're going to have to do all kinds of neat science. What kind of science do we do, and how do we train the astronauts to get ready to do that? Let's find out from somebody that's actually trained astronauts. Hi, I'm Jim Green, Chief Scientist at NASA, and this is Gravity Assist. This season is all about the moon. With me today is Dr. Kelsey Young, a planetary geologist at the Goddard Space Flight Center, whose specialty is in the development of handheld instruments for the exploration of Earth, the Moon, and the Mars environment. She also has experience in training of astronauts for future missions to the Moon, Mars, and beyond. Welcome, Kelsey.
Thanks for having me.
Well, how did you ever get involved in this concept of training astronauts?
I actually got involved back in graduate school. My PhD advisor was involved and was nice enough to get a couple of his graduate students involved. And I went out with the 2009 astronaut class and have been involved ever since.
Wow, that sounds kind of neat. How many were there?
There were actually astronauts in that class from NASA, the Canadian Space Agency, and from the Japanese Space Agency. So we got to work with a whole different variety of astronauts.
What's important about training astronauts in science prior to a flight?
Astronauts train in a whole variety of subjects prior to flight, and it's exciting that we get to train them in science as well. They train in systems for the International Space Station. They train in how to operate the robotic arm. They learn how to fly T-38 aircraft. But we also get to train them in science, and the reason that's important is actually for a couple reasons. When they're on the International Space Station, what are they doing besides the onboard science experiments? Well, they're taking pictures of Earth. They get a lot of time to actually look out the window, take pictures of what they see, and make broad-scale observations that scientists on Earth just don't have the perspective to make. So we want to train them in those scientific processes so that they understand what it is they're seeing when they look out the window, and that they can take pictures that are valuable to scientists back on Earth and help us here learn about Earth system processes. And it's also important to train them in planetary science. And, they're out there answering questions to the public, and we want them to know what NASA's driving planetary science questions are. And then, of course, relevant to what NASA's doing right now, we want to train them in the big picture lunar science questions, the big picture Mars science questions, and we want them to get excited about the science that they're going to be doing one day on the surface of the Moon and Mars.
Sure, of course. I mean, when you think about it, they have to know everything about what it takes to survive in the harsh environments and the different environments that they experience, the weightless environments. And then once they master that, then that next step is, what can we do in that environment? And that has just been such a fascinating topic.
Absolutely. So in Earth science, we teach them about land cover and land use and oceanography. We talk about natural disasters, and you've often seen astronaut photographs from when there's a big hurricane coming over the Houston area, for example, and astronauts kind of understand what those processes are from a macro scale so that they really can understand what they're seeing. We also kind of get into the specifics of planetary science. So we take them sort of on a tour of the solar system, so they're familiar with all the planetary bodies and what the driving science questions and the NASA missions are right now that are teaching us about these bodies. And then we get into a little bit more detail even on the Moon and Mars. So we talk about the major geologic provinces of the Moon and the major science questions we have left. We talk about impact cratering and volcanoes and why those processes are dominant, not just on our planet, but across the rest of the planets. We talk about Mars science and astrobiology and teach them why it's important to look for life elsewhere and what we're even looking for when we're looking for signatures of life elsewhere. So we try to make them ambassadors of all of the big picture science questions that we at NASA have.
Well, it sounds like, the astronauts are in classrooms, but that's not entirely correct. Aren't they out in the field?
Yes, absolutely. So they actually, we spend about equal parts in the classroom and the field. So actually, when I talk about, training astronauts in science to school kids, I make sure to let them know that it starts in the classroom. So what those school kids are doing in the classroom, one day astronauts are doing it too. So we teach them about the fundamentals in the classroom, but then we absolutely take them into the field. And we actually get to take them in the field a couple times. So So we teach them how to geologic map. That's something that I learned back when I was an undergrad geology student, how to produce a geologic map that tells you something as the person reading it about what formed the area that the astronauts are exploring in. So we teach them about how to produce those fundamental tools of geology. And with that comes field experience and understanding tectonic processes that build mountains and volcanic processes that erupt lava flows onto the surface of our planet. And then we also take them out into terrestrial analog sites. And what that is sites on our planet that look something like sites on the moon and Mars and other planets. So they get to develop their plans, looking at their field site of where they want to go and actually execute that traverse based on what they see in the field, similar to what they're going to be doing on the moon and Mars one day. So we get a lot out of those field experiences, but it all starts in the classroom.
So you get outside, you really, understand what the environment is like, these terrestrial analogs.
Absolutely. Analogs are everywhere, and analog is something that's like something else. And in this case, we're talking about places on Earth that tell us something or mimic some condition to a planetary environment. So we train underwater because that simulates the lower gravity conditions in space. But scientifically, analogs are an area on Earth that is shaped by a process that's similar to a process we see in outer space. So, for example, we go out to volcanoes on Earth that mimic something about volcanoes on the moon, or we study impact craters on Earth that look like impact craters on Mars. And by learning about those dominant planetary surface processes here on our planet, it tells us a lot about what we're seeing in images and rover data and orbital data from other planets.
Kelsey, what's a day of astronaut training like when you're out on an analog site?
Sure. Yeah. For science training in the classroom, we're doing activities as well as just, lecturing at them about science. But in the field, it can be pretty dynamic. Typically, we're camping. So we wake up and we make breakfast and we get our packs ready for the day. It's really kind of, also having them experience expeditionary skills. So what it's like to live and work in a team environment and actually, do science in that team environment. And then we, go out to the field. So typically, the groups of astronauts actually drive the day. So they have objectives to create a geologic map, run a traverse plan, and collect a representative sample suite. And they get to plan how that day gets executed. So as trainers, we typically, are there as a resource, but we also want them to drive that day of exploration. Then in the afternoon, when they're done with that day of hiking around the field area, they actually, they debrief about how that day went, what they learned, how the samples they collected fit into their big picture geologic story. And then, of course, we have, camp maintenance things like, making sure your gear is stored properly and out of the way, cooking dinner. But typically, it really focuses around exploration and having the astronauts drive their own field experience. And then at the end of the week, we actually have them debrief to the trainers about what they learned in the geologic map that they created.
Well, some of those analogs are really remote.
Yeah, they're all over the world. I studied several impact craters in Canada, so that's near and dear to my heart. And you're right, those are remote. Those are really hard to get to. They take a lot of logistics and overhead. There are others that are kind of right in our backyard. I did my PhD in the state of Arizona, and there are volcanoes and actually an impact crater as well right there that tell us a lot about volcanoes and impact craters. So we see analogs that are valuable in not just training astronauts, but understanding planetary processes all over the planet. And we have quite a lot that have been used extensively right here in the U.S. Hawaii is a wonderful planetary analog. It's so volcanically dominant. There are so many volcanic features that tell us so much about volcanoes across the solar system. We planetary scientists have been studying in Hawaii for a long time. Volcanoes all up and down the west coast of our country teach us a lot about different types of volcanism on other planets. So we really see these exciting planetary analogs right here in our backyard and also, as you said, remote places like Australia and Canada.
When we look at the moon and it's cratered everywhere, these are from impacts. These are from asteroids that have come in and hit the moon and blown a hole in it. And you make it sound like they're just everywhere around the Earth. But, they're kind of hard to find. They're not that easy. And the reason why, of course, is the atmosphere and the weathering and the changes that we have here on our own globe. But these impact craters that you find, how big are they?
Absolutely. And you make a good point about that. Impact craters are a lot harder to find here on Earth than they are on the moon. On Earth, we just have a couple hundred that we're able to visit, whereas on the moon, there's orders of magnitude more than that. And they range in size. So Meteor Crater is an iconic crater here in the United States, and that's quite small. It's less than a couple kilometers across. We also have impact craters preserved on Earth that are a couple hundred kilometers across. My work has focused on impact craters that are somewhere in the neighborhood of 20 or 30 kilometers across, so kind of right there in the middle. But you make a great point that, we can study impact cratering processes here on Earth, but the best place to do it is on the moon. It hasn't been eroded by water or much wind over the surface. There's not active plate tectonics that can erode those processes away. And that's actually one thing we train the astronauts. It's a wonderful objective to go to the moon to do because we have a lot left to learn about impact cratering, and it's hard to do here on Earth.
So when you go out with an astronaut, are they wearing a spacesuit, or is that necessary all the time?
So when we are in the field with astronauts, especially when we're doing their base level science and geology training, they're not in spacesuits. They're just in shirt sleeves, just like we kind of do when we're doing field geology work here on Earth. And that's really because we want to focus on the science fundamentals. We want to make sure they have the kind of backbone training in geology that they need to be great scientists on other planetary surfaces. And to do that, we want to kind of focus on the science. We at NASA also have a series of analog projects where, you're right, the astronauts wear spacesuits in analog environments to train them about how to actually operate in the confines of a pressurized environment while they're doing, planetary surface relevant tasks. But for, baseline geology training for the astronaut classes, we really stay away from having them interact in a spacesuit just because we want them to focus on the science.
Well, how similar or different is it the way we train astronauts today versus what we did during the Apollo missions?
During the Apollo missions, they got a lot of science training. It's often said that the Apollo astronauts who flew to the surface of the moon had the equivalent of a master's degree in geology by the time that they flew. And in fact, one of the 12 Apollo moonwalkers was, of course, a geologist, and Dr. Harrison Schmitt. But the training that the new astronaut classes receive now is actually pretty similar. It focuses actually in similar field sites. We go to very similar field sites that the Apollo astronauts visited. But when an Apollo astronaut was actually assigned to a mission, their training turned to site-specific analog training. So, for example, when the Apollo 15 astronauts flew to Hadley-Rill, the geology training focused on analog environments that mimicked Hadley-Rill in some way. And we envision future Artemis astronauts having a same sort of training portfolio of getting that background of really rigorous science and geology training before then turning to analog operations in an environment that mimics their landing site in some way.
Artemis is our major program going forward that's going to visit the moon in a series of missions and getting ready for ultimately visiting Mars. So it's a pretty spectacular program involving astronauts going to the moon. We haven't identified where exactly on the moon our first Artemis astronauts will be walking. But as soon as we do, then the training, as you say, will shift and be far more specific. What I like about the concept of going to the South Pole for our Artemis astronauts is it's going to be very different view than what we saw with the Apollo astronauts. And part of that is because of the sun angle. Because we're in the southern hemisphere and in the South Pole in particular, that sun is going to give us these long, really bizarre-looking shadows. So it's going to be really neat. I'm really excited about that.
But that brings up an interesting point about how to train the astronauts in that. So how do you, they're used to doing science, on Earth, and their, analog environment training where they have just the lighting conditions that you and I are used to here on Earth. How do we train them in science with those drastic illumination conditions? It presents an interesting challenge.
It really does. I mean, and then they're trying to identify certain material to take back. I know Harrison Schmitt on Apollo 17, he saw these beautiful orange glass beads and talked about it. Even Houston didn't believe he was seeing these things and brought them back. And we learn a lot when we do that.
Yeah, so the trick is, at any landing site, you want to collect a representative sample suite. So you want to make sure you get one of everything to simplify things. But you also want to be able to identify when something is different and unique and it's something you didn't expect. And, in the orange beads example, that's exactly what happened. He didn't expect to see that. He recognized that it was something unique and exciting and potentially, scientifically really valuable, which of course it turned out to be. And, given his background in geology, he was able to completely, jump all over that and collect the sample. But first and foremost, we want to understand a landing site, characterize it, map it, and get a sample of every unit that's there.
Well, one of the things that's a big difference, I'm assuming, you'll have to tell me, is that when we trained the Apollo astronauts, they had certain tools and certain instruments. But today, we have much more sophisticated instruments. So, what kind of new instruments would we expect them to use?
An issue near and dear to my heart. Yes, for the Apollo astronauts, they had, as you said, just basic sampling hardware. They had rock hammers and scoops and tongs and sample containment bags. But as you said, in the decades since Apollo, geologists now are using spectrometers that can tell you what a rock is made out of, or geophysical instruments that can probe the subsurface and tell you what the units underneath your feet are. And we envision future astronauts having comparable capabilities.
One of the things that we did in the Apollo mission, and we only did this a few times, was to take a core, so it's a hollow tube that you jam into the soils and as far as you can, and then cap that and then pull it out. And it might be a couple feet long, and it shows in depth of what's going on underneath your feet. I think we didn't do that enough, and I would really like to see us do that in the Artemis landing sites. Don't you think that's a great idea?
Absolutely. And NASA just chose to open previously unopened core samples because we were excited about what they could tell us back from when the Apollo astronauts collected them decades ago. So lots of exciting core work going on now.
Yeah, I agree. This is just really a wonderful opportunity for us to be able to get ready for our first woman and our next man stepping on the surface of the moon coming up in 2024. Do you have a favorite question you want answered as scientists then are roaming on the moon?
I guess if I had to pick a favorite, I'd say get that sample from the South Pole Aitken Basin. So by actually getting a rock back from the moon, we can get it into a lab and understand exactly how old it is. And in the case of impact cratering, that tells you something about when that impact crater happened. So you can actually date multiple events, like when the rock crystallized, and then different chronometers or dating systems can tell you then when that impact happened in relationship to that lifetime of the rock.
Yeah, now some of these impacts are larger than others. So by getting rocks from them, we can actually even say, okay, there's a size distribution that occurs over time. And that's really important to understand how the solar system evolves.
Absolutely. And the moon is the best place to get those samples to understand impact cratering as a process and how it affected the inner solar system. And that's because kind of the moon has sort of been a witness plate for the rest of the inner solar system. On Earth, we have plate tectonics, water erosion, people, vegetation. The moon, we don't have any of those active surface processes. So to understand impact cratering as a process, the moon is the place to be.
Well, you mentioned another type of analog, which is water. And that actually is something I know something about because when I first worked for NASA in the early 80s at Marshall Space Flight Center, they had a neutral buoyancy tank. So I became a neutral buoyancy diver, and helped the astronauts and also the engineers that were developing a variety of things. But that's centered around spacewalks. That's centered around repairing instruments. That's centered around, doing what we call extravehicular activity. But now these water activities are more like what one might do walking on the moon.
Absolutely. So we actually do still, of course, at NASA have the Neutral Buoyancy Lab, but it's, of course, now at the Johnson Space Center. And they do train for the EVAs or extravehicular activities that the astronauts do on the International Space Station. But we also train in other aquatic environments, as you say. So one example is the NEMO, or NASA Extreme Environment Mission Operations Test. And that is using a facility owned by the Florida International University, the Aquarius Reef Base. So it's an underwater habitat off the coast of the Florida Keys that astronauts and scientists and engineers and habitat technicians live in for a couple weeks at a time, mimicking the conditions that astronauts live in on the International Space Station or one day in a lander on the surface of the moon or Mars. And so they live in there with their crewmates, and they actually conduct these simulated extravehicular activities outside of the habitat, similar to what we'll be doing one day on the moon and Mars. Of course, they're studying corals and sponges instead of rocks, but sampling those corals and sponges actually uses similar hardware to what the astronauts will be experiencing on the moon. So by understanding a core sampling system that can sample corals and sponges, we actually make advances in the core sampling technology for moon rocks.
So you've been out in the field on these analog sites a lot. What's the most unexpected thing that happened at an analog site?
Probably it's anything pertaining to logistics. So the science is always exciting and you go in with questions and, a sampling plan to address them, but Mother Nature does not always behave. There was one memorable field campaign that was about 5 or 6 weeks in, remote Canada, and had, a bear incident, a hurricane come through camp, a hole in the boat we were using to get out to an outcrop to sample. And it's just, sometimes nature just doesn't behave the way you expect.
Well, fortunately, none of those things will happen on the moon,
That's
but
right.
indeed. When you're out on these field sites, do you really feel like you're in space sometimes?
Analog environments can absolutely feel like that. When I'm a support diver for the NEMO project, which has NASA astronauts living underwater. And there's something kind of really fun and exciting about seeing the astronauts out on their simulated spacewalks in their sort of simulated space suit, operating, using a drill that is in development for use on the lunar surface and seeing them do that underwater. There's definitely moments where you sort of have out of body experiences about, how amazing that is. And I've certainly had that scientific moment several times in analog environments where you're on a volcano and that one day it's, the weather is a little bit weird and you have the feeling that it's, an environment that's not quite of this world and you're there to study out of this world planetary processes. So I certainly have those moments. And when there was one day in particular in Hawaii on the Big Island where this crazy fog cloud came in and we didn't stop work because, it wasn't dangerous in any way, but the fog is so thick that you can barely see someone when they're 10 feet away and you're doing science, you're collecting samples, you're learning about volcanoes on other planets. And that was, a pretty trippy day, really exciting.
Well, Kelsey, I always ask my guests to tell us what was the event or person, place, or thing that got them so excited about planetary science that they decided to move in this direction. I call that a gravity assist. Kelsey, what was your gravity assist?
For me, I got into planetary science through geology. That was sort of my entrance into this world. And I got into geology probably in 4th grade when I went on a hiking trip with my dad and my sister. My dad, demanded that we try one hike, and I was not into it. And he said, fine, you can wait in the car. And I was so indignant that he was going to leave us in the car that out of spite, I agreed to do the hike. And I was hooked from then on out. I just was completely in love with geologic terrains, hiking in them, learning about them, interrogating them. And when I found out that I could do that on other planets, I was hooked. That was it. I was totally hooked.
Yeah, it's really a neat concept, to think about how other planets are made and their relationship to the Earth. Kelsey, thanks so much for joining me on Gravity Assist.
Thanks for having me.
And all my listeners, remember, this has been a fabulous 50th anniversary as we have celebrated the moon over all these gravity assists. But next year in 2020, we're moving on, and we're going to be searching for life beyond Earth. I'm Jim Green, and this is your Gravity Assist.